you going to model in SolidWorks or directly in ANSYS?
I can use in ANSYS.
Okay, so please show us ANSYS. I want to create a cylinder. 圆柱, create a cylinder.
Okay.
So over here, you can see on the left-hand side, we have so many module. Each module can operate a kind of finite element analysis. So he chose, what did you use? Static structure? Yes,
static structure.
He chose static structure, okay? When you say static structure, that means it's not a dynamic problem. If you are working on a dynamic problem, then it's rigid dynamics. But he is only using static load. So inside the static, what did you do? Double click?
Yes, okay. You can double click
the module.
Yes.
Okay, so he double clicked the module, then inside this area, this is like your working space. You can get rid of the second one. Yeah, remove. So he put one module here, and if one day you need to work on multiple modules, for example, if you have, if you have a liquid channel, and then you have liquid flowing. You don't need to do anything. I'm just explaining to them. Let's say you have a liquid channel and the liquid coming through, and inside, let's say you have a structure. Then you need to, if you want to analyze the liquid and also analyze the structure, they are two different kinds of physics. Okay? So this is solid mechanics. This is fluid dynamics. So over here for ANSYS, it has fluid dynamics right here. You can put that in the working space, and you can solve for solid and fluid separately, and then combine together. Okay? Can you operate this? Okay, so but today we are doing very simple things, just one kind of physics. But in the future, you can try to work on multiple physics. So usually, if you are working on multiple physics, for example, the deformation of solid requires information of the shear stress generated by the liquid. Then there are some interaction between at the interface of the solid and the liquid. ANSYS can handle this kind of simulation. Okay, but that's more advanced. We don't need to do that today. So, okay, Alan, what's next? Define geometry, right?
Yes.
So over here, you can you 往前一步? Hold on. So inside the geometry, make a click on the geometry. Yes, now click. Okay, and then, okay, show us how to do it.
And choose the
new model. Okay, new design model. Okay.
Yes.
Okay, do it. So this is not SolidWorks, not Pro-E, not AutoCAD. This is the CAD design platform generated by ANSYS. It's not the best CAD designer, but it could be used. If you want to design your own geometry in SolidWorks, it's okay. You can complete your ANSYS or your SolidWorks or Pro-E design and then import into the module. Okay, so please create a cylinder for us. Do you need to draw a circle first?
Okay. Here we can.
You can just choose. Okay, good. So primitives means simple geometries that is predefined by the computer. So cylinder is a primitive, and you can directly choose it. Okay, let's build a cylinder. Okay, can you build another one, a thinner one, next to this one?
Okay.
Yeah. The radius, okay. Yeah, good. That's good. Can you make them longer?
Yes.
Okay, okay. Yeah, that's fine. That's fine. Okay, so yes, let's complete like this. And can you make the first cylinder longer? Is it easy to do it? Cylinder 1, okay.
Yeah.
Change the length. Okay, 3 is good. Okay, okay, good. So this is okay. Do you need to add the material right now?
No, not in here.
Okay, so over here you create geometry. Very good. Do you go back to the module? Okay. Next, what you need to do is to choose the material, right?
Yes.
Okay.
You can edit the material in the engineer data.
Okay. So can you show us? Let's change to copper. Copper tone.
Okay.
So right now, by default, it was steel. Usually we work with steel. Can you choose? I think you can find copper somewhere. It should not be composite. Just try general material. And you scroll up, you should find copper. Copper alloy. Okay, let's use copper alloy. So from ANSYS, you can already see a lot of known material inside ANSYS. Okay, let's try copper alloy. Okay? So how do you assign copper alloy?
And in here we need to go the model.
Okay.
In here, then can assign it.
Okay, show us. Alan, when you do everything, do it slowly.
Okay.
You are doing too fast because we cannot see you. We cannot see your mouse movement. Do
Okay.
it slowly, okay?
Okay.
So what do we do?
In here we can open the geometry,
Uh-huh.
and here is a solid.
Okay.
And go down to the detail. Here is the material. We can choose it to change it.
To copper alloy. Okay, good.
Okay.
So from outside, you need to add the material you want to use in the library. Because ANSYS has so many materials to use. So from outside in the module, you can choose the material you want, and then inside this definition, you can then select the material you used. Okay, good. What's next? Do you create mesh right now?
No, not yet.
Okay. What's next?
We need to. We can choose the mesh in here.
Okay. Yeah.
And
I think you can. Okay, so what is a mesh? Mesh is basically cutting this whole thing into small elements, just like what I showed you last time. And when we select mesh, usually there is a parameter that allow you to have bigger element or smaller element. So what is the property for mesh size? Can you show us? Sizing? Yeah. I think it's sizing.
Sizing. And here we can insert the sizing to set the size.
So what is default? 预设 what is default?
Default
Can you at the left lower?
is
Yes.
over here.
So let me see. Mesh or resolution is default. Resolution default.
Yes.
Can you try to change it? Resolution.
Default.
Yes. So right now the default number is 2. Can you use the default? Don't do anything and then oh, we already have the mesh.
Yes.
So this kind is more like a triangular shape, but it's not triangle. It's I forget the name. 四面体 What's a 四面体? Okay. Basically, if you cut inside, basically it's like our 粽子, right? Okay. So let's try to change the resolution to a greater number. Okay, and I think you need to solve. So now you can see they become smaller. The element, can you change it to, let's say, 5? So we can see the difference and solve. Okay, then from here you can see the element size becomes so small. Okay, so let's try to use 2 for now. Use 2. Okay. So by default, it was 2. Okay. Now the next thing you need to do is to define boundary condition. Okay. Hold on. Let me tell them what is boundary condition. Okay, so remember on Monday we talked about F vector, K matrix, and degree of freedom, right? Degree of freedom vector. So usually when you define a problem, for example, let's say we are going to fix this upper right corner to the wall, and we are going to apply a force right here. Fine, can Alan see this? No, right? Can you take a picture and show him this is what I'm going to do later on? And let me explain first. So if you do this, that means there is one node right here, right? So if our coordinate system is like this, if this is x, y, and z, then we have a force. For example, if this is node number 23, just for example, then for computers, it knows f node 23 along z direction, there is a negative force. And there's no other force on this node. So in that case, F23, X, F23, Y, they are both 0. Should be 0. Actually, it may not be 0. Because you only know this one. You are not sure if there is force along Y, X, and Y. How come you are not sure? Because there are internal forces. If I apply, this is external force. External force. Okay? If I apply external force, in between, inside the material, there are internal forces. So over here, some force will be applied to this node. These are internal forces. Okay? And we don't know how large those are. Finite element will solve it. So if we assign this boundary condition, we are sure one of the number, this one, fz23, we can only be sure about one of the number. Okay? And all the rest, we don't know. And when we assign boundary condition right here, like this one, we claim it's fixed on the wall. So for example, this is node number 12. In that case, because this is fixed, we are sure U12X, U12Y, U12Z, they are 0. Because you say it's fixed. So in this case, there are 3 numbers here. They are U12X, U12Y, U12Z. They are all 0. So inside ANSYS, some information in the F vector will be known based on your formulation, based on your assignment. Some information will be known in the degree of freedom vector. So what ANSYS will do, ANSYS will try to solve for these 3 numbers, the corresponding 3 numbers. Because if you have those 3, and you have 3 equations, you can solve for the 3 unknowns right here. Okay, and ANSYS will then try to solve for every other information later on. Basically, the software will try to solve for all the internal forces and all the degree of freedom. Okay, so by solving this entire equality equation. Okay? So if you assign the boundary condition correctly, it should simulate what's going to happen. If you assign the boundary condition incorrectly, then ANSYS can still solve it. However, it will be wrong. So it's very important for you to assign the boundary condition correctly. Okay? You need to assign those exactly like the real world. Okay? Okay, so Alan, did you already got my picture?
Yes.
So on the right edge of the entire cylinder, please fix them on the wall. Just
Okay.
fix boundary condition. Do it slowly.
Okay.
So I think it's called a fixed support.
Yes.
So apply fixed support, okay? Apply to the right.
And choose
right,
here.
Yeah, right surface. Okay, and then say apply. Good. Now assign single force. But how do you do it?
I right separate it. And here I have the force.
Okay.
We can choose it.
But this one applies a force on the surface, right?
Maybe. I think I can choose in the
Surface only.
yeah.
So, can you choose a point? Oh, component. Okay, okay. Try. Can you apply to a point? Maybe from the on the left geometry, you need to select, because for computers, it needs to know which point. You don't have a point.
Yes.
Okay, then just use the shear force. Apply to the surface. That's fine. Okay. So it's okay. He's going to change the problem. Assign, yes. Is it on the surface or on the node?
On the surface.
So okay. So if you want to assign a force on the node, you need to let the computer find the node. But in his geometry, there's no point right there, no point object. So for easier demonstration, today he applied the force onto the entire surface. So in this case, this is a shear force, applied to the entire edge. Okay, so try to solve it.
And what force we need is it?
Oh, you mean how do we want to see? Okay,
Yes.
please show displacement, stress in every direction, and Lami's stress. Oh no, the force just going down.
Going down, okay.
Going down, yes. Okay, negative 100 Newton. Okay, good. So for the solution, can you turn on this deformation and say directional? Okay, and one more. Stress, say equivalent Lami's. Okay, and one more. Stress again. And this time you can use maximum shear. Maximum shear. Yes, let's try to see this. One more. And stress. That's C. Just. I want to see stress along every direction. Oh, anyway, okay, now from here you can make sure you check the unit. This is a millimeter, and this analysis basically, I think it shows you the maybe not even the nodal information. It shows you everywhere. And it will highlight the information by color. And over here, the maximum deformation is 2.0 to the power of negative 6. So this is 2 times 10 to the negative 6 millimeter. So what is that? It's a 2/3 micron. So it's a 2 nanometer. So there is a 2 nanometer deformation right here. So very small. Is it nano? Yes, nano. Right. And what is the minimum? The minimum is negative 2. So negative 2 nanometer. And it's right here. And this one is right here. The largest one is right here. So right at the close to the edge. But is it correct? Maybe not. So Ellen, let's try to make our mesh smaller.
Okay.
This time change it to 5. Okay. Solve
Okay.
again. Okay, and let's check deformation again. So at the end, it's 1.9, 1.93, also nanometer, and pretty close position. Can we try even smaller? Let's try 12. Oh no, 10. How about 10? Let's try 10. Okay, the maximum is 7. That's okay. Let's try the smallest. Yeah, the maximum is 7. Okay, and let's see deformation. Deformation? Okay. So, okay, 1.94. And similar location. So I think it's pretty good. Okay, let's take a look at stress, equivalent stress. It's too, I cannot, it's really hard, very hard to see. I think it's at the, on the top, is it? No?
Over here.
Okay. It's very, because it's in, I think it's close to inside of the material. Okay. So let's keep this number. We previously see 2 nanometer displacement, and the von Mises stress is around 0.004 megapascal. Okay, so it's around 4 kilopascal. Okay, this is what we have. Okay, Ellen, can you go back to CAD design?
Okay.
Back to our geometry. Okay. Let's do 倒角, around. So can you make rounding? Okay, please try to.
Like this?
But not there. 那个转角那边.
Oh, okay.
So go back.
Over here?
Yes, exactly. Yes. So, yeah, can you make it larger? Maybe 0.3. Okay, generate. Okay, now go back to analysis. And yeah, you can directly update and solve. Okay, directly solve. Do you need to remesh? It's okay, you will remesh, but you will remesh. Okay, good. And then let's see the formation. So max deformation now reduced to 1.8 nanometer. And okay, it reduced 1.8. And let's see principle, the equivalent stress. Now is 9.5 kilopascal. So you can see if you have rounding, then your deformation reduced and the stress reduced. Okay? But is it accurate? Over here at the corner, usually you have stress concentration. So maybe it's accurate, maybe it's not. It's very difficult because even for research, sometimes we try to study stress concentration, and we know the software may not be accurate enough. Okay, so but you can use it as a reference. Okay. Okay, good. Let's make it more interesting. So Ellen, can you go back? Can you see the maximum shear on the left? 最大剪力. let's see where is the, okay, also same place. Okay, let's see maximum principle. Okay, go back to maximum shear again. So maximum shear, let me copy it. Tau max is 1.9 K Pascal. Yes, and that's the maximum principle. So this is the maximum principle. Should be, okay, this is a 3.8 kilopascal. And this is von Mises. Okay, now we can take a look at every model we have learned. So we know maximum shear stress model tells us your largest shear needs to be smaller than your Young's modulus over your safety factor. Okay? And your safety factor will be, sorry, there's a divided by 2, right? Yes, 2, for shear is divided by 2. So your safety factor would be 2 times this, okay? And this equals to around 3.8. Okay, this will be your safety factor. And from here you can tell, very similar to over here, very similar to your maximum principal stress. Because they are basically, they could be determined from the same Mohr circle. That's why the value right here and the value right here is very close. If you use normal stress, then your normal stress needs to be smaller than your Young's yield strength over safety factor. So at the end, you have same model. These two are the same. But how about von Mises? If we use von Mises, then it's a little different. Then we have 3.5. This is smaller, and we will see greater safety. How come? If we use von Mises, we have greater safety. Can someone tell me? Does anyone remember? If we use principal stress or shear stress, the number right here is 3.8. But when we use von Mises, the number here is 3.5. That means when we use von Mises, we have greater safety. Who remembers why? Anyone? It's in our second part of our exam. Remember?
Because the commission stress is more conservative. Oh no, more liberal.
More aggressive.
More aggressive.
More aggressive. Yes. Yes. Remember, there's a when we work on the model, there's a model like this. Thank you for your answer. This is our maximum shear stress model. And this is for plane stress problem. This is the stress in the first direction and second direction. And for maximum shear, we have this this shape. And for maximum, the other model is maximum distortion energy model. And this one is based on von Mises stress. And when we introduced this model, we said maximum shear is more conservative. And on the other hand, the maximum distortion energy is more aggressive. Okay? So that's why if we use von Mises stress, the estimation of your safety is higher. You are not conservative. Okay, so please try to combine what you learn with what you work on in the future. And you need to make your own decision. Do you believe in von Mises stress? Or do you believe in shear stress? If you are conservative, you need to use shear stress to estimate your safety, because your safety is lower. So if you one day in the future in a company, your supervisor asks you to design something, and you need to know your safety, then you need to question yourself or question your colleague. Do you want to be more conservative or less conservative? Remember, different models indicate different results. When you use von Mises stress, you are more aggressive, less conservative. Okay? Always remember that. Okay, Ellen, let's try something fun. Let's go to our model. Go back to the model. Can you 挖一个洞? Can you make a cut vertically? 垂直从上面挖个洞，随便挖。So it's an extrusion of cylinder but cut. 应该是挤出 cylinder， 然后但是是用挖的，可以吗？Oh, you need to make a drawing. Okay, okay. I think he's nervous. He doesn't say anything. Don't be nervous, okay? Are you nervous?
No, it's okay.
Okay. Yeah, just okay. Draw a circle. Yes. Somewhere. Okay, that's fine. Can you make it larger? Okay, so he draw a circle on this plane, a little larger. That's okay. I think that's fine. If you okay, make it 0.7. 0.7. Point. Yes, yes. Yes, I think that's nice. And make a cut. So, Alan, continue. 我解释一下. So let's try to cut away this material, make a through cut from top to bottom. Continue. You can continue.
Okay.
Yeah, I just talked to my students. So if we make a cut, a through hole, this structure will become weak, but of course become lighter. We will observe what's the deformation and what's the stress. How does it look like later on? Okay. Did you? Okay, good. You already cut through this structure. This structure can be seen everywhere. Then you will realize a structure like this will be weakened a lot. Okay, let's go back to analysis. Let's solve everything by same parameters. And let's now take a look at deformation. So where is large maximum deformation? Okay, it's right here. So the place that has larger maximum deformation changed. It's not at the original place. It changed to here. Because this structure becomes so weak. And let's see how large. So this is 1.64. So basically, basically 16.4 to the 10 to the times 10 to the power of -6. So this would be 16.4 nanometer. So originally, the maximum deformation was 2 nanometer. Now it becomes 8 times larger because you drill a hole. Okay, let's take a look at stress. Okay, equivalent stress. So the corner has the largest stress, and then we can see it's 0.01 megapascal, so it's 10 kPa. It was 3.5. It was 3.5. Now the stress become 10, 3 times larger. 3 times larger stress at the corner, and also the location changed. Alan, can you 看一下刚刚的位置? So previously, I think it's over here. This location was the place where we have the largest stress. So 这个是可以分析，是不是？分析点吗？
自己做选区，我
It's okay, it's okay. We can check the color actually. So if you check this area, this is where we have largest stress. And the stress level is around this region. So it's around between 2 to 3 kPa. So similar to what we had earlier. It didn't change much for this area. Or it could be even smaller stress. Because right here, it becomes so weak. All the shear force generated here is trying to create bending at this position. Okay, and over here, the original place, the stress becomes maybe a little bit lower. Okay? So, Alan, are you able to do fluid dynamics easily? Is it easy?
No.
It's not easy, okay?
Okay.
If we create a very simple fluid domain,
Maybe I can try it.
yeah, that's a separate problem. It should be easy.
Okay.
Okay, so let me show you if we want to a fluid problem. Okay, so yeah, ANSYS, thank you. You can turn this off. Okay, and you can close the structural module. You can delete module A. Okay, yeah, you can delete. I will tell you what to do.
Okay.
So now let's try, hold on. Try fluent, the second one. Yeah, try fluent. Okay, so how come there are many different kinds of fluid flow? CFX, fluent, poly flow, what does that mean? ANSYS is a huge company. Fluent was a smaller company. But Fluent, when I was a PhD student, I used Fluent. I didn't use ANSYS for my PhD. When I graduate, ANSYS purchased Fluent. So Fluent become a part of ANSYS. And you can already use Fluent inside ANSYS. Okay? So now, Alan, please try to create geometry. So if you want to model liquid, what you need to design is the area of your liquid. So Alan, can you design exactly same thing? 就是两个圆柱一模一样 exactly same.
Okay.
So what we are doing right now, we are just like modeling a pipe, the area inside the pipe. Okay, so right now what Alan is doing, he's modeling the empty area inside the pipe, 管子内部. Okay. Okay, that's good. So let's imagine this is what's inside the pipe. This is where your liquid is. Okay, now you can go out. Okay? You can go back. And the most important thing is boundary condition. Let's go to your model setup. I think in setup.
Okay.
Okay. Now, for the most important thing is boundary condition. But let's see what is the material. 这种材料, or is it? Is it air? Let's see.
We did not define it yet.
Okay, so change to fluid. Change to fluid. Yes, so now this whole thing becomes fluid. And go to material, see what is that? Material. Only here, okay.
Okay.
Okay, let's assign a new material. Let's change to water. Can you?
We need to
Okay.
include it outside.
Okay, let's go outside and then pick up water. Can you? Are you able to? 就像你选那个材料清单那样子。
这个功能没，我不知道为什么它没有在里面。
Okay. Try new material. New material. Hold on. Refresh model cell in the project after creating new. Say okay. Okay. Just say okay. Okay, never mind. Just don't do anything. Just let it be liquid. Okay, now can we try maybe mesh? What do we do? Let's generate. How do we 怎么建边界条件 boundary conditions?
好，那个是在下面的。
Okay.
在那边。
Okay. Let's try to do boundary condition. Okay, this is fine. Okay, let's try setup. Okay, hold on. Okay, 3D problem, good. Just start. Just by default. Okay, this is something new. I have never seen this. Okay. Okay. The resolution is difficult for us to read. 解析度就太难。materials 左边 left fluid. Okay. Okay, I think the resolution is too small. 那个解析度太差了，所以看不到。
对不起。
I mean, change resolution first. Okay, this is a new interface. I have never seen this before. 你调一下解析度，电脑。
好，我再调。
1 to 80. But eating. Okay, try this. Okay.
Maybe I close this first.
Okay. The most important thing should be set up. 现在就定边界条件就可以解了。 Okay, general. Okay, just say okay. Okay, good. So boundary conditions. 左边 boundary conditions. Yes, boundary B boundary.
Found it out here.
Yeah. Say 你选择 wall， 第二个 wall。OK wall solid OK。第二个。对不起。OK just say OK。OK。You need to pick up. Let me see. 你在左边有一个 wall， 里面有一个 wall， 看一下。OK wall solid 它已经是 wall solid OK 不要管它了，那就是we need to find inlet。inlet mesh interface， 再下一个 mesh interface yes。auto create try auto create。two zones between boundary from boundary zones。麻烦了。Okay, turn off. Okay, I think this is going to take too much time. I didn't ask him to try this before. It's okay. Then maybe we just go to internet and look for one solution. That's faster. Go to internet.
Okay.
And say CFD result. CFD. And say result. RESU. And result. ULT. Yeah. Do the other. Okay, and then find pictures. 图片 just 图片 yeah. Okay, scroll down. 往下 Let me find something similar. Scroll down, continue. Maybe 继续 Okay, good. Okay. So this is I think this is like a fan, and it's simulating what's inside the fan, and you model the fluid domain. Sorry, usually a simulation like this takes a lot of time to set up, and I didn't tell my student to prepare this, so it will take too much time for him to get ready. But usually what happens is, if you have a fluid domain, for example like this, you need to tell the computer the boundary conditions. For example, this could be inlet, and this could be outlet, and this could be the wall. And you need to specify what's inside the material, inside the pipe. You can say, okay, this is water. Okay, so then for the inlet, you need to specify what is the volume per unit time to represent the speed of the fluid. And then you need to cut this whole thing into mesh. And usually for fluid, it's very complicated. You need to specify the wall conditions, such as, do you have boundary layers? Have you already learned fluidics Fluidics. You guys learn fluidics, right? 流体力学.
Is that an app or
No, the course.
fluid mechanics?
Yeah, fluid mechanics. So you must have learned something called boundary layers, right? Do you remember this figure? You guys remember this, right? Fluid dynamics. Nobody replied to me. This is inside the boundary layer. So the velocity, over here, the velocity is 0. And this is like the velocity of the stream. This is velocity of the stream. And inside the boundary layer, the velocity changes from u goes down to 0. Okay, and if you want to simulate a fluid domain, the software needs to simulate something like this. The velocity close to the wall is almost 0, and the velocity at the middle is the highest. Okay, and at the end you can see, Alan, 你这右边这个图下面有一个那个流线图 ，yeah, this one, yes. So you can see the streamline, okay. Alan, 你有没有我那个心智图那个网站 ？Task， 对 ，Task， 去那个 Task， 没有。我贴 ，hold on。
好。
Fine, do you have it? The web page for the mind map. I want to show the students some of my previous results. Sent to Alan. Do you have it? Oh.你问他谁有那个网址啊？
好，问一下。
Okay. I have it. Hold on. Let me paste. Okay, go to the link. And go to, let me see.右上角 fluidics, upper right fluidics. And go up. Fluidics, yes. And then turn on the third one, console 2011 from the top, console 第三个 COMO 超链接点一下。Okay, scroll down to find the pictures. Okay, so this is a heat sink, 水冷散热 heat sink, using water to cool down CPU. When I was a master student, we designed this to cool down CPU. So in Fluent, actually we use another software. We model the liquid domain inside. So water comes from the top and then goes out from the side. Okay, 往下 go down. So this is This is how we define the boundary conditions. Okay, go down. Okay, stop here. So you can see this is called streamline, 流线. So from the inlet, the liquid comes down, and you see a lot of vortex right here, and then goes up from the outlet. Okay, and from here you can tell this is temperature distribution. The purpose of this is to cool down the CPU. So the heat, this is at the center, the CPU is right here. The heat is being taken away to the side and then goes out. That's why the entire heat sink is cold, it's not hot. 这是一个水冷散热 liquid comes in at the center and take out the heat. Okay, continue, go down. I think we have several different designs. Go down. Okay, no more. Go back to my map. My map. Okay, let me find an interesting one. Let me see. Hold on. Okay. 有一个 ERAC 2015 ERAC 上来一点，好，是不是？再往上 ERAC， 耶，这个左边，没错。go down. Continue， 继续。Okay, we truly made the heat sink. Okay, go down. 往下。Okay, go down, up. So we even make this by 3D printing because we know when the liquid goes in and come out, the heat will be taken away. This heat sink is cold, it's not hot. So it could be made by plastic. Okay, continue to go down. Okay. More. Okay. Even more. There's no more. Okay, boring paper. Okay. 换一点. This one is too boring. Okay, 上面那个 FEF. 看看 maybe more interesting. Okay, 往下. Yeah, this is done by the final element. Okay, go down. Okay, we try different shapes inside the channel. So when you work on your project, you can try different geometry. Use final element to see the results. So just like what we did. Okay, but at the end, the result tells us the cooling efficiency didn't change much. Okay, 换一篇. Okay. 那个右上角有一个 ANSYS， 往下2015，往下一点，再往下一点。对，这个。Maybe more interesting. Go down. 一直往下。Go. Okay, very boring paper. Okay, 换一个。So, let me see which. There's one is very interesting. I try to find that one. Where is it? Ah, 有个绿色的 TW 2015. Try this one. Go down. 没有图片。Okay, there's no picture, sorry. I couldn't find it. But anyway, so in the past, finite element truly help us to simulate the performance of a device. So in your project, no matter what you're working on, you can start to make design, you can change your design and see if you can make it better. And I can teach you what you can do. Because later on when you try to improve, Alan， 那我们今天就这样子，感谢你。Can we
OK， 谢谢老师。
say thanks to Alan? Thank you. Let's clap our hands. Alan, 谢谢 Thank you.
谢谢老师。
Okay, bye bye. So,
拜拜。
so I want to talk more to you, tell you more about your project and what you can do later on. So now, let's say you have initial design or current design. Okay? No matter what it is, what you need to do is to identify the function variables. So what are variables? Variables are something you can change. Okay, so for example, if your design is the cylinder that Alan just showed you, right? And let's say the variable that you can change is the round, the radius of the round. So let's say R is your variable, okay? And next thing you need to do is maybe you need to figure out some functions. So what do you mean by functions? Some functions are like performance of your design and or factors. Okay? In this case, one of the performance of this cylinder will be stress or deformation. Okay? And maybe weight. Okay? So if you have variables and you have several functions, the next thing what you want to do is change the variables. When you change it, you will see whether those functions become larger or smaller. So in this simple case, if you make your radius larger, of course become heavier. This will become heavier, but it will become stronger, so the deformation will be smaller. And the stress will become smaller. Okay? But when you try to increase the radius, there's always a limit. And usually it's called a constraint. 限制 constraint. Right? Your design limit. So you can only design within the limit. So maybe your R can only be smaller than a max number or greater than a minimum number. Maybe R cannot be negative. R cannot be 1,000. R has a range. So what you can do is try to change the variable, change the value, and see the performance. And in your mind, you need to know, do you want this to be smaller? Is smaller better? When the stress is smaller, it's good, but it becomes heavier. Heavier means more expensive. So you need to make a decision. Okay? Of course, the process of this can be done by something called optimization. Okay, but I will not focus on optimization because it takes some time to learn how to do optimization. I will give a lecture of optimization in 111-2. It's a graduate course and also given in English. So if in the future when you have a problem like this, you really want to know how to use optimization to find the best design, of course you can come and take the course. But for this course, all you need to do for now is to identify the variables and figure out what are the key functions. Make sure you're concerned about the constraints. And what you can do is to just try different numbers. Computers are very convenient. You can try different numbers and compare. Okay, so what you can do next is try different variable values and compare. Okay? So in your project, you don't need to know any optimization methods. You can just identify the problem, try different numbers, use the software to see the difference of the performance, and then pick up the best one. Okay? So that will be the project. How you can achieve your achieve what you want at the end of the project. Okay? Everything okay? So starting from next week, you guys need to work on the project with my students during your free time. About the lecturing, I will go back to our textbook and begin to introduce some important components, such as spring design, bearing design, gears, and pulley. Usually I like to introduce components that is related to a cylindrical system, because I believe in a machine you always have a cylindrical system, because you usually have a motor, and the motor usually is connected to a cylindrical system. And you will have bearing, gears, pulley, belt, and spring, and so on. So I will begin to introduce those components and what's the design behind it, which means we focus on the stress analysis inside the component. And I will tell you in the future, when you are truly making a design and need to make a decision of one of the components, should I choose a larger bolt or a smaller one? Okay, fine. Can you show the picture of the AGV they show in the group yesterday? Yeah, I just want to show them. So yesterday my students were building the AGV in our lab. Let's take a look. In Facebook. No, just go to Facebook. Oh, it's already here. Okay. Okay, thank you. So the size of the vehicle is 2 meter long, 1.7 meter wide, very large. It's like a bed. You can lie in a bed. It's a moving bed. Okay. So over here, like this is the wheel. There's a cylinder right here, and there are two bearings. And this is where you have your motor and decelerator. So it will. Is it called decelerator? I'm not sure. No, it's called the harmonic drive? I'm not sure. Okay, anyway, it reduces the speed of your motor. And the red one is so-called the connector that connects to axle system. The alignment, the axial alignment is so important, but it's very difficult to achieve perfect alignment. So the connector in between is important. So when the first student built this, how did she know this connector should be in this size or this number? Should I buy a bigger one or a smaller one? That's the key of mechanical design. And like when she chose the bearing, why 2 bearings? Why not 3? Why not 1? That's the key of this course. Okay, I can show you her thesis. Her thesis is all about mechanical design. So in your project, I wish you will be doing similar things. Okay, let's wait. It's very large file. Let's see. Okay, maybe we can read through this. This is her thesis. Okay, like right here. The goal of this vehicle is to carry a robot arm and grabbing a heavy object. But the robot arm needs to move toward front without falling. So she needs to make force analysis to make sure if there's a heavy payload in the front with certain distance, this is not going to fall. This is basically a basic force balance, okay? But where are the, well, this is the design. I think I showed this to you earlier. Did I? Did I show this to you? No? Okay, not in the class. Oh, her PowerPoint is ready. Okay, good. Okay. So like this, it's called a coupling, okay. And this is the shaft she designed. There are 2 ball bearings, and there's a huge wheel, okay. And this is your motor. So when she designed this bearing, she knows what's the total force that this bearing needs to carry. So at the end, the company tells you how much load this bearing can carry, and she figured out she needs to put 2 sets of this bearing in order to carry the entire load. Okay? And for the rubber coupling, the connector, because it's the connector that transmits the motor torque to the wheel. So this device definitely needs to carry the torque generated by the motor. So there is a graded torque provided by the manufacturer. So she also needs to calculate, okay, what's the maximum torque this motor is generating, and this has to be chosen properly. Okay, this is exactly what you will be doing in this class, ANSYS. This is also done by ANSYS. So just like what Ellen showed us, a stress analysis. So she was calculating the safety factor, and she was using maximum shear stress model. This is basically maximum shear stress model, just like what you have run. Okay, so she designed this shaft to make sure it's carrying everything, and she figured out where is the maximum shear stress, and then the safety factor was 6. So it should be very strong. Okay, and she also analyzed the entire the base plate and apply all the loads on top of it, and then try to figure out where is the maximum stress. And the stress distribution looks like this. And she also calculates the safety factor based on different models. Okay, from here you can tell von Mises stress gives greater safety factor because it's less conservative. Maximum principal stress is right here. Okay, then this is the maximum shear, just like what we have learned in the class. Okay, and the rest are just about control. If you are interested in this vehicle, I can show you a video. This is a vehicle that can move from side to side, and also can spin by itself. Okay, I think one of the group is working on this. Is it HEV? Yeah. Okay. So your group will be experiencing something related to this vehicle. It's already assembled back in my lab yesterday night. Yeah. Okay. Okay. So the purpose of today's lecture is to share with you how you can use ANSYS to do analysis, and then kind of give you a guideline how to do your project. Okay? And from next week, we will be going back to component introduction. Okay? That's it for today. Thank you.